Okay, this video is going to be matrix multiplication. This is an exciting one. We're adding a big new tool to our toolbox. It's gonna sort of expand a lot of what we can do, and of course give us a lot of interesting things to think about and properties to look at, and so on. So I'm definitely excited about that. And let's dive right in. So I'll start with what I might think of as the traditional definition in terms of sums, and then we'll sort of draw some pictures and try and make some sense of it a little bit. But the general definition of matrix multiplication is if you have some matrix A that's m by n, and you have some matrix B that's n by p, and you're going to multiply these together, you get some matrix C that is m by p. And each individual element of this matrix C over here, you'll have, say, for example, Cij is equal to the sum across n of A, I need to give this a name. Let's say K equals 1 to n of Aik times Bkj. Okay. So this is the definition of matrix multiplication. But just looking at this, it's probably not super helpful. One thing you might think about is, if you can recall from when we described matrix vector multiplication, we had, let's say we had some vector, let's call it V, just to distinguish. The vector equivalent, we would have said V sub I is equal to the sum across K of Aik x sub k, right? So there's definitely a similarity there, but I think the easier way is to think about that as, so this was again, if you have matrix vector, right? Is to go back to sort of our helpful diagram here. So when I was talking about matrix vector multiplication, I drew it kind of like this, right? Where here's our matrix, and here's our vector, and then here's our output vector, right? And I said each element here is the inner product of this vector with this row over here, right? So these things all multiplied together, and then these things all multiplied together to get this one, and so on. The only thing that's going to change for matrix multiplication is we're essentially going to treat the right-hand matrix as just a big stack of column vectors like this, okay? And then similarly, the output, well, I'll get back to that in a second. The output is also a matrix now, like so, right? So if my overall thing here is C equals A times B, right? Then each element in C, here's A, here's B over here, right? Each element in C is the inner product of some column of B with the relevant row of A going across this way, right? So it's exactly matrix vector product, but just each column of C is doing a matrix vector product with that column of B, right? So the very upper left of the output C is the inner product of the first row of A and the first column of B going that way, right? And then the second, if this one down here is the same column of B, but with the second row of A. This one over here is now the second column of B with the first row of A, and so on, just filling out the whole thing, right? And so a couple of things. So before I said M by N, and this one is N by P, right? Let me see if I can fix this a little bit. This one is M by N. Sorry, I hope this is not too small to see. This one's N by P. Then this one needs to be M by P, right? So in our diagram, what that means is that here's A, it's M by N, right? So M rows, N columns. Here's B, it's N rows, P columns, right? And now it kind of makes sense the way this lines up. These N's, they have to be the same, right? Because the inner products have to work. These inner products have to work here. So the number of columns in A has to match the number of rows in B, or that won't work. And then the output, well, this one also lines up. This is M because this is M. This is P because that's P up there. You see that? So the N dimension, the sort of inner dimension of the matrix multiply, gets in some sense squished away into matrix into the output matrix. And we can see some special cases of this that will help us to sort of familiarize ourselves. One that I already mentioned is if we do matrix vector multiply. Well, matrix vector multiply, that's exactly the same as matrix multiply, but imagine now that X is an n by 1 matrix, right? And A is same as before, m by n. So sort of following our rule here, we know that C should be m by 1. And that makes sense with our definition, right? The only thing that changed in our picture up here is this P dimension is 1 now. So it's like we're taking, let me see if I can change the color without. Okay. So if P is 1, then that means this matrix just looks like this, right? But everything else looks the same. And it's again, we've just got this, and we've got our standard matrix vector multiply, right? Okay, so let's think about, one thing that might be sort of fun to just think about is, well, what happens if we make the other various dimensions 1? If we make all dimensions 1, this becomes scalar multiplication, and there's no problem. There's no problem with that. If we make M1 instead, so we said when X is 1, our picture looks like this now, and we get matrix vector multiply, right? When P, this was the case where P is 1. Now let's try making M1 and see what happens. So now I'm going to say C is 1 times P. A is 1 times, and I have some N here, and then this one is N times P this way, and I could call it X. Maybe it makes more sense to call it B, just that's more consistent with the others. I don't know, we'll think about that in a second. But okay, so now I have my A, that's sort of my left side, that's now been changed into a 1 by n, like that, right? And my B, that's still a matrix, an n by p matrix, right? N by p. And my output is now a 1 by p again, right? So this one also looks like a matrix vector multiply, but in some sense like sort of turned on its side, right? It sort of turns it into row vectors. So if I were rewriting this as vectors, I might write something like C is equal to A transpose B, something like that. C transpose maybe, to emphasize that they're row vectors and not column vectors. Which brings me to a point, I don't remember if we talked about this when we first talked about matrices, but if you have some vector, we can think of vectors as these sort of n by 1 matrices, right? Which means that if you take the transpose of it, you end up with a 1 by n, which is in some sense sort of a row vector, right? Which is exactly what we end up with here. And we'll come back to that thought in a minute too, I hope. I always say we come back to it. I'm not sure how often I actually do come back to it, but that's good. Okay, so we look at what the shape of it looks like if we shrink p to 1, we just get matrix vector multiply. If we shrink m to 1, we get this kind of matrix vector multiply, but it flipped, vector matrix multiply. What if we shrink n to 1, right? What if we shrink n to 1 here? So now I'm going to say C is equal to, okay, so I'm keeping m and p. So C is equal to m by p. Oh, right, we're on it. C is equal to m by p. A is equal to n by 1. And B is equal to 1 by p. This one's actually an interesting one, I think. So now we've said A is a regular n by 1 matrix is kind of what we usually think of as a vector, right? Here's our A, it's n by 1. And now we've said B has only one row, right? But P columns. This is B over here. And our output matrix, C, is then n by p. So this one is an interesting one. These are, in some sense, it's kind of like we got out vectors, or we put in vectors but got out a matrix. But the matrix is a very kind of simple matrix in some ways. So if you think about, in this case, for example, let's think about like C11. C11, it's the inner product of this row with this column, right? But each one of those elements only has one thing in it. So if we think of them as vectors, then C11 is A1 times B1, right? And in general, Cij is just AI times Bj, right? And this actually has a name. It's sometimes called the outer product to sort of contrast it with the inner product. Outer product. So the and like the inner product, as we've known and discussed many times, takes in two vectors and turns them into a single element, right? So inner product, let me scooch down here for a second. So inner product, you have something like U transpose V, U transpose V, and that turns the U sideways into a row vector, leaves the V as it is. And our diagram works just fine in this picture because then we end up with a 1 by 1. If this were matrix multiply, it would just be the case where both M and P are 1, right? U is in some sense a, if we say U is n by 1 and V is n by 1 matrix, then U transpose is a 1 by n matrix, right? And so we get 1 by n times n by 1, and the output is 1 by 1, right? So that's inner product. The outer product, similarly, you can think of it kind of the same way. Like, let's say I have, well, I called them A and B, so let's call them A and B over here just to think about it that way. Let's say I have two vectors A and B. This time, unlike inner product, they don't have to be the same size. So I'm going to say, you know, A is in, I need to try and keep it consistent, it's in Rn, and B is in Rp. So A is an n vector and B is a p vector, right? And then I say, A times B transpose instead of U transpose times V like I did over here. I'm going to say A times B transpose, right? And that's going to give me, so A is an n by 1 and B is a p by 1, so it flips around to be 1 by p. And so my output, you know, C if you like, is this n by p. It's this n by p matrix, where each individual element is just the product of its respective elements in A and B. Whew, okay. So this is kind of a lot. I actually want to, I think, let's stop here and recap, and then I'll do another video where let's do one simple example, just like concrete example to help sink it in. And then we'll do a second video that's the overall, that we go through some more of the properties. So let's see. So we're going to have some matrices A and B. This is where I miss having a real class, because I'd love to just ask for some numbers here. First of all, how big should they be? Let's make I don't want them to be too big because I don't want to be here forever. Let's make A 2 by 3. Okay, so 2 rows, 3 columns. And then I definitely want to put some zeros in there because, again, I don't want to be here all day. But let's say 1, 0, 2, and then -3, 1, 1. Okay, so now if A is 2 by 3, what size should B be? Well, we know that it has to be 3 by something, right? The number of rows have to match the number of columns of A. So, so I'm going to say it's 3 by, and then what do we want it to be? Let's make it 2, I guess. So it's going to be 3 by 2. So we need, I don't know, 1, 1, 0, 2, 1, 0. Again, I'm trying to not make my math too hard on myself here. Okay. And then we want to say, what is C if C is A times B, right? And again, A is 2 by 3, B is 3 by 2, C is going to be then 2 by 2, right? So I'm going to set up my little chart here. Let me actually copy and paste. Okay. So so I moved them over just to make a copy here. So here's A, here's B, and my C matrix is going to be right here. And I'm just going to, for each one of these, I'm just going to do the inner product, right? So I'm going to say 1 times 1, that's 1, plus 0 times 0, that's 0, plus 1 times 2, that's 2, right? So so then I get 3 as this element of my C matrix. And then down here, I'm going to do first column of B with second row of A. So negative 3 times 1, right? Plus 1 times 0, plus 1 times 1, right? So we get negative 3 plus 1 sounds like negative 2. I think I did that right. And then now for this place, I'm going to do first row of A, second column of B. So I need 1 times 1 is 1. Whoops. 1 plus 0 times 2 plus 0 times 0. So that's just 1. So that's easy. And then last one, we're going to do second column, second row. So negative 3 times 1 is negative 3, plus 1 times 2 is 2, plus 1 times 0 is 0. So I get negative 1 here. And so that, get some of these things out of the way. So that's the answer. That's the matrix multiplication. And again, each column of C is just as if we had done that column of B with times A. Each individual element of C is just the inner product of those two. So yeah, so that's an example. Hopefully that that makes sense. We went through kind of a lot here, but there's a lot to cover. We went through the sort of formal definition, and talked about how it sort of looks on the diagram and the different sizes and what happens if you shrink or change certain pieces in the outer product. So big picture here, I think the most important thing is we're adding this new thing, matrix multiply. It works exactly like matrix vector multiply, but each column of the output matrix is matrix vector multiply with the column of the right-hand side. And the sort of big units check that you need to do in your head is just get used to this m by n times by p is m by p. This, let me go way up here. This. I actually think this is maybe the first thing to just like hammer into your head right here. The inner units have to line up. The outer are the result. All right, great.